Hello, my name is Steve Perkins. I am the Chief Marketing Officer and Head of Product for a company called Beva. We have a new solution that we've introduced to market for TLS visibility, decrypted visibility, that works for TLS 1.3 as well as legacy, and we call it Symmetric Key Intercept. I'm very thankful for the opportunity to present it to you here today. So let me jump into it. So as I mentioned, we have a technology for TLS visibility. We call it Symmetric Key Intercept. We are in the business of developing and licensing the software. We license the software to end users as well as to now a growing suite of manufacturers. We've made an announcement about a month ago about a major cybersecurity manufacturer who's licensing this technology to embed in theirs. We expect to see more. We offer it, therefore, through manufacturers as well as direct to end users. The promise or the advantages of this approach, let me just kind of hit high-level advantages, is the ability to see into any and all traffic, including TLS 1.3, including in both inline and passive applications, to be able to do that with better price performance, as well as reduce latency, as also to simplify things architecturally and operationally. And the net benefit, of course, of that is increasing capability to you, ultimately end users, to be able to see into your traffic for various needs, typically cybersecurity or application performance monitoring, and at the same time to reduce costs, both operational as well as capital costs. So let's jump into this. So the problem that we address is that there is a need for most organizations to look into their TLS traffic to see their payload, but the traditional methods have a growing set of issues. And those issues typically are capability, price performance of scaling, and or complexity. Now, if you look at the three pictures down below, there's three fundamental methods that are used to look at traffic. Man in the middle. I'm assuming you all understand these, but I'll just cover them high level. Man in the middle, where we're rewriting certificates. In this case, we actually have blind spots around PIN certificates and difficult protocols and applications. There's huge price performance consequences of this mechanism. And ultimately, the industry, in many ways, folks like Google are moving to thwart it and shut it down because ultimately, in many ways, you could think of it as a security violation. The second is termination. We try to we load certificates and server certs and move the server onto some offloaded system. We terminate the sessions up front. We send them and we inspect the traffic. We either re-encrypt or bridge it back into another encrypted tunnel. But at the end of the day, this exposes clear text on the backbone. We have, again, certificate management complexities and security issues. And ultimately, this requires certificates. So in the growing world of cloud, the ability to actually look at traffic where you're not the server, which is a growing part of cloud applications and cloud use, that's actually doesn't work. And lastly is, of course, RSA or handshake replay, where we're loading and replaying handshakes to regenerate the keys. And of course, we all know this doesn't work with perfect forward secrecy Diffie-Hellman. And again, requires certificates and all of that jazz. So as we sought to solve this problem, we said, let's rethink the problem. Let's look at what we're trying to do. We're trying to inspect traffic either inline or out of band. Well, decryption itself is easy and efficient. It's built into every chip. The hard part is actually getting the keys. If you have the keys for a session, decrypting it is very, very simplistic and efficient and low cost. But all those other mechanisms go through all sorts of macerations to try to ultimately get to a key to decrypt traffic. So we asked ourselves, what if? What if you could get the session keys a different way? And this was born, again, from a Diffie-Hellman-based world. How do you do this? So we said, well, the keys exist. They exist in the memory of a client and a server while the session's alive as a result of that handshake. So why not, the simple idea, why not capture and reuse those keys that you've already generated, that you've spent the money, the cost, the complexity to generate? Why not capture, reuse them, harvest them to fuel visibility systems? And why not make that system into a commercially viable solution, meaning it's reliable, it's scalable, it's secure, and ultimately doesn't disrupt architectures, it's easy, it's economic. That's ultimately was our design criteria for building what we call Symmetric Key Intercept. Now, this method, this idea is not new. You can log keys in many different ways on a standalone app server here or there. into Wireshark, whatever it may be. The challenge is doing that at scale and commercially. And that's fundamentally what we solved. So Beva introduced Symmetric Key Intercept about a year ago, announced it with AWS, actually, as they announced their VPC traffic mirroring. But the solution works for cloud and data centers, whatever it is. And ultimately, what we do is we deliver a set of software in the form of next generation agents, endpoint agents that are agent technologies. There's a whole suite. I'll cover that in a second. And what they do is they can capture and help you reuse those symmetric keys from either the client or the server in real time. So it can grab those keys, et cetera, and help you distribute them to either inline systems like a next generation firewall or an IPS, or to passive systems like an IDS system or an application monitoring system, or ultimately even send them off into a key archive, a secure escrow of sorts that allows you to match session keys with PCAPs, stored PCAPs, for forensic analysis or lawful intercept downstream and after the fact. So let's dig into this one level deeper. The core of our technology we call sensors. So these key sensor technologies work as follows. If you look at the picture on the right here, basically we know that sessions, actually the handshake is conducted by either the client or the server using a piece of TLS code in memory. And it generates that key and then decrypts traffic into the application that needs to see it or that's generating that session. Now, what we produced is an agent technology, essentially, that learns and extracts those keys from TLS processes in memory. This is the core of our IP. And what it is a read-only memory tracer function that you can load either on the client or the server side, or both. It can work on either side of the connection, which is a new thing that frees you up from the need to understand certificates and deal with certificates. How it works is this. You load the system, you give it permission to read memory. It is not a hack. It is something you have to specifically and explicitly permit to read process memory. And what it does is it scans the system to discover TLS processes. And when it does, it loads highly efficient signature algorithms that understand how to decode those processes. And then what it does is it waits to see a client hello at the beginning of a handshake. When it does, it knows where the final symmetric key will be placed in memory associated with that client random or that session, and ultimately copies it and exports it. And the beauty of this architecture is it works regardless of protocol. It works with TLS1.3. It actually can capture all the interim keys that decrypt the handshake itself, as well as the final secrets. It can actually work against legacy, TLS 1.2 with PFS, doesn't matter how, cipher, handshake, et cetera. This works across libraries and protocols, et cetera, and it's extensible. We could talk about that in the QA, but the ability for this platform to extend into other protocols has actually been proven, and we'll be rolling those out. Today, we are focused purely on TLS. And the last part of this, as I mentioned, it's only needed on one side. So if you are trying to secure a data center, place them on servers, not endpoints. If you're trying to monitor traffic from endpoints going to the internet, you can place them there as well. The last part of this is that this is extremely high performance. This is not massive memory scans. This is not like an antivirus system that burdens the system. We have perfected the mechanism through this platform. It's really a platform architectural approach for how to decode TLS processes in memory. And with it, we can extract a key within 200 microseconds of the time it's created. That is to give you a sense to understand that. That's before we can get our hands on the key, after it is generated, before the handshake completes, and before the first packet is sent. And to give you a reference benchmark, you could take an AWS C5 extra large, a moderate-sized system. We can actually capture, it's capable of about 600 sessions a second. We can capture all the keys. And when we're doing that, we use about 28 meg of memory and far less than 0.5%. I think at one time we spiked to 0.5% CPU core on that. So this is a silent listening device that can essentially, as I said, help you harvest and reuse those session keys. So let's move forward. So these sensors, we have sensors for Linux, We have them for Windows servers back to 2012, and we're going back in time on that in the coming quarters. We also have released recently Windows Desktop, so S-Channel is all applications there, as well as Chrome, Edge, Chromium, et cetera. We can capture keys out of all of that, Dropbox, et cetera. In doing so, we actually become the first company, I believe, that can actually intercept the keys and help you decrypt PIN certificates such as Microsoft 365 or Dropbox or what have you. Now, we also have the ability to run as a container inside Docker, as well as inside Kubernetes environments. In Kubernetes, the recommendation is to run, and we support running as a daemon set. So that means that a single instance can run on the baseline nodes underpinning your clusters. We also have OS X, Android, and iOS in development as part of our roadmap. Now, once you have keys, we've got a reveal problem here. Once you have the keys, what can you do with them? Well, the sensor can write them to a local file, so you can use them for diagnostics like something like a Wireshark. On the left, you also can pipe them programmatically with APIs and open APIs, and we also license source code. And you can actually modify the source code to integrate with a localized application or an agent, for example, a host-based IPS. You can also export these via HTTPS or DTLS. We've recently released for a fast path to basically export the keys to external systems. So now we can forward keys off to inline systems like a firewall or an IPS or a web gateway, or we can forward them off to a passive system and enable decryption on an IDS or an app monitoring tool, or ultimately even off to appliances and packet broker systems that do decryption. Finally, they can actually be logged off into key archives and escrows. We also support another mechanism for scale and scaling and cloud applications, which is to send this to an interim key buffer. We call it a key depot, which actually can be used to push or for pull or push-based applications to allow keys to be served to multiple different systems in real time in parallel for scale out, scale up, scale down applications as well. So there's one last thing here, I think cleaning up some last pieces. We also offer a symmetric decryptor. This is a containerized generic symmetric decryptor, general purpose. It reads inbound packet streams. It pulls and matches keys with them, or can have a local Flask-based simple KeyDB on board. And ultimately, it can either receive packet streams or ultimately PCAP files and matches them with those keys and decodes. So these actually can be deployed as standalone decryptors if you wanted to roll your own decryption appliances, again, for scale up, scale down on commodity hardware, or ultimately embed them on tools or systems that don't have effective decryptors or decryptors at all. Again, delivered as a Docker container allows modularity and an isolation of the process against other systems, a very simple, easy implementation. The symmetric key intercept approach can ultimately enable many, many different applications and systems. So taking it one level deeper, we don't have a lot of time to go into all the use cases, but the symmetric keys can enhance and boost inline systems. As I mentioned, with the ability to get keys before the handshake ends, those keys can actually be landed on firewalls, gateways, inline devices before the first encrypted packet arrives. Allowing dramatic performance boost by offloading or augmenting or eliminating man-in-the-middle processes. It allows you to see the traffic that you can't, like PIN traffic, and ultimately simplifies all the exception management and the tinkering you have to do around difficult applications. For passive systems, this is really simple. We restore or enable TLS1.3 or PFS-based, perfect forward secrecy-based inspection with 1.2 on those systems. By feeding those keys. And many of those systems can actually receive symmetric keys, or it's built in their core engines. If not, again, we have the symmetric decryptor. And ultimately, because of the simplicity and the universal nature of this and the ability to actually see client-side connections, meaning you don't have the certificates, east-west traffic is now a possibility. Monitoring Kubernetes and service meshes is now a possibility without having to stick inline bottlenecks everywhere. So the idea that we can restore existing systems, supercharge them, and extend their life, as well as open up greenfields, is the promise of this approach. So that's really it. Symmetric key intercept. Again, as I mentioned, we license this technology to end users as well as to a growing set of manufacturers that you'll start to see announcements coming. We would love to talk to you about it if you're interested. It is ultimately a new approach, a new method. Manifest as a set of software that can help you see more traffic, go faster, be simpler, ultimately to increase your capability and lower costs. So that's it. Thank you very much for your time. I'd be glad to field any questions.